Hi there guys, I just wanted to explain this diagram here at a jacaranda. This creates a little bit of a problem just when people go through this, so I just want to take you through this. So I want you to keep in mind that what we're looking at here is we're looking at generators. You'll notice here that I've got a coil turning. You'll also notice here that I've got a magnetic field running across. I hope you like my Star Wars pointer. So magnetic field is going this way across the page. That's what these two dashed lines represent. There they are there, there they are there, there they are there, etc. And then I've got the coil represented in two orientations. So I've got like this 3D view here going all the way across so you can see the coil rotating. And then what I've got here on the bottom is I've got, again, this is a side-on view. So if you see LK there, then you can see LK here. And you'll notice at this point in rotation that this part here, LK, is actually parallel to the magnetic field. So because it's parallel to the magnetic field, there's no EMF induced. But you will notice in this case that because the coil's face is open right up and it's 90 degrees to the magnetic field, you've got maximum flux. Okay, so let's have a look down here. In this case here, I've got maximum flux and I've got zero EMF. So I've got maximum flux, there it is there, flux, and I've got maximum flux, and I've got no EMF because it's parallel. No EMF. Okay, let's have a look at the second diagram and see what's happening here. So once again, remember this is a generator, not a motor, so we're putting kinetic energy in to get electrical energy out. So if we look at Mn in this case here, if you like, this is lifting up now. Okay, well, if you like, if you want to follow KL around, KL is come around to the other side now. Okay, so if we have a look now, what we've got is we've got magnetic flux through the coil at 0, but what we've got is we've got side KL with maximum cut of the flux. So if you like, KL, the current carrying conductor, is at 90 degrees to the magnetic field, so it's got maximum cut. Over here, 0 cut, not cutting the magnetic flux at all. Here, totally cutting. Maximum cut. So in this situation, we've got 0 flux through the coil. Okay, let's have a look. 0 flux through the coil, but we've got maximum EMF because we've got maximum cut. There it is there. Okay, so one of the things to try and understand, and if you like you can follow the rest of the diagram through, what you'll notice is that if we look at the flux through the coil, it's maximum, minimum, and it's maximum in the opposite direction, because if you like, if you consider this coil rotating, it's then flowing through the back of the coil when we go around this way, so it's flowing through the opposite direction to what it was initially. And you can see that by the orientation of LK at the top and then at the bottom there. Okay, so I'll get you to do that in your mind's eye as you're rotating the coil. If you watch the other videos, you'll see that as well. Okay, so if you like, going again, diagram 1, maximum flux, 0 flux, maximum flux but in the negative direction, 0 flux again, and then we've got maximum flux again. Now to determine the EMF, you can actually use Lenz's law, and I've put Lenz's law in over here. Now remember, Lenz's law, to determine the EMF, the minus sign signifies that it's the negative rate of change of flux with respect to time. Now the way I think about this is like this. So what I say when I'm doing this is I say, well, let's have a look now and see, and you'll see if you consider the flux here initially, there's my tangent, and if you like, the gradient of that tangent that I've just drawn, you'll find is 0. And so if you have a look down here, there it is, 0. Okay, now if we go along here and we draw a tangent here at that point there, and I know it's terribly drawn, the math students will really be upset with that, there's a rate of change of flux there. Now you'll notice there that the gradient of that tangent is negative. Okay, but remember there's a negative sign over here in Lenz's law, in the EMF law, which Lenz says it must oppose the rate of change. So if the maximum gradient there is the maximum negative gradient, then over here, if you like, we must have two minuses which make a plus. So there it is, plus. Okay, so the second graph, if you like, is negative gradient of the tangent of the first graph. Say that again. This graph here, if you like, is negative the gradient of this graph. So I'll just quickly fill it in. Okay, if you like, what I've got now is, if you have a look here, I've got a 0 gradient there. There's my 0 again. Got a positive gradient through there. Positive gradient there. But I've got negative of that if I look over there. And so there's my negative there. Okay, so rate of change of flux with respect to time. The negative rate of change of flux with respect to time gives you the EMF.